reading a review topic this time by Professor Barry Barish. Our esteemed speaker today, Professor Barry Barish, is an American experimental physicist renowned for significant contributions to multiple areas of high-energy physics. Professor Barish began his academic journey with a bachelor's degree in physics at the University of California, Berkeley, where he went on to complete his PhD in 1962. Following a year as a research fellow at Berkeley, he joined the California Institute of Technology in 1963, later becoming a faculty member in 1966. During his time at Caltech, he played a pivotal role in high-energy physics experiments at the Stanford Linear Accelerator Center and Fermilab, and was among the first to observe the weak neutral current, a fundamental aspect of the electroweak unification theory. In 1994, Professor Barish became the principal investigator of LIGO. 3 years later, he helped transform LIGO from a partnership between Caltech and MIT to a large international consortium, establishing the LIGO scientific collaboration. Under his leadership, the LIGO detectors were significantly advanced, ultimately leading to the historic first detection of the gravitational waves on September 14, 2015. Professor Barish was awarded the 2017 Nobel Prize in Physics alongside Professors Rainer Weiss and Kip Thorne. Since 2016, he has received numerous prestigious honors, including the Enrico Fermi Prize, the Henry Draper Medal, the Giuseppe and Juana Cocconi Prize, the Princess of Asturias Award, the Fudan Zongzi Science Award, and most recently, the National Medal of Science awarded by President Biden in 2023.
This meeting is being recorded.
Physics and Astronomy at the University of California, Riverside in 2018, where he continues to inspire the next generation of physicists. We are delighted to welcome you, Professor Barish, and we are truly honored to be in your presence.
Hello, everybody. It's morning in California, so I may start a little slowly. I'm going to try to share my screen, and then I'll tell you what I'm going to talk about today. The host is disabled screen sharing, so I can't share it until somebody lets me. Can somebody let me share the screen?
Are you able to do it now?
Yeah, I can't share the screen. Somebody has to let me share the screen.
Just a moment. I think it should be possible.
Okay, I'm now somehow not on the first slide, but okay. Let me get back to the first slide. Okay. All right, we're ready to start. Hello, everyone. As I said, kind of as I was turning on this morning in California, I guess evening in India. I'm going to take you on a short journey this morning or this evening, where I'm first going to, for people who aren't familiar, review a little bit what we have to do, what the whole process of doing gravitational waves is about, through what it took to make the first detection. And then I'm going to cover the gravitational waves is about, give you kind of a preview of where I think in the long run, maybe not just for gravitational waves, but in general, one of the most important areas of physics, astronomy, actually cosmology will develop over the coming period, and the role that will be played by gravitational waves. And even there's a hint that may be starting already. So on this first slide, you just see a very crude picture of the history of the universe. We know from measurements of the expansion rate of the universe that the universe is 13.8 billion years old. And in this crude picture, it starts with the Big Bang. It actually starts with what we call the hot Big Bang, which is means it started not like some things at low temperature and then build up, but it started as a very hot bang that created eventually that energy turned into particles, and particles eventually turned into atoms and things that can make up eventually nuclei and pretty soon combining them together, stars and galaxies and so forth, and then we have the world that we have the universe that we have today, 13.8 billion years later. So first, just review LIGO a little bit before we talk about the early universe. The picture on the left is actually the drawing that was made by the Nobel Committee to represent what the whole thing was about, and it's a pretty good summary if we're just trying to pick one slide of what's been done. So the picture, the little wavy lines going along the sides in the shape of an L is an interferometer. That interferometer compares the time it takes for light to go down one arm and come back compared to the other arm and come back. If the times are equal, the signal is inverted, one with respect to the other, and nothing is detected in the final detector that detects any signal that comes through. If one arm gets a little longer or shorter than the other, then they come back out of phase, and some light comes to the detector, and by analyzing that light and as a function of time, we're able to see gravitational waves. But the picture on the right is a picture of exactly that. The scale is the most impressive thing. First, you'll see the scale on the left, if you can read it, is called strain. That's in gravity, the equivalent of the wave function in electromagnetism. It's the fundamental strength of the interaction. And the scale is 10 to the minus 21, which you can barely read on this graph, but that's the scale. So the number 1 here is 10 to the minus 21. So that size of the effect is 1 part in 10 to the 21, and that's an incredibly small number, and why it took so long and was so difficult to measure it. We are able to measure it by the magic of a very sensitive instrument, an interferometer, but a very special one, which I won't describe in detail today, but just a couple of features. Its sides are large, not like in a laboratory that you have in a school. It's 4 kilometers on an arm, and there's many features of it that are made to make it very, very sensitive. It's driven by a laser beam. The laser beam comes in, divides, and sends light in 2 directions. If the 2 arms are exactly the same, the light that comes back will exactly cancel. So the picture on the right is actually the very first detection of gravitational waves. It's the picture that was in the publication, the physical review letters. You'll notice the strain is 10 to the minus 21, as I said. And the picture on the top is what's happening as we move along. In the left, we have 2 objects kind of spiraling in toward each other. In the middle, they're actually merging, and to the right, they've actually merged, and then it rings down a little bit. This was the very first detection. There's 2 different lines drawn. One is for the interferometer in the state of Washington in the U.S., and then the second one in the state of Louisiana. The confidence that what we detected was real is emphasized by the fact that it was detected in 2 different detectors, 3,000 kilometers apart. So if we think of gravitational waves, we can kind of, if you haven't studied general relativity, or if you have, this equation should look familiar to you in either way. It looks, what I've done is formulate general relativity. I'm not going to talk about it in detail today, but the paragraph here describes it, what I did, what assumptions I made, but I've done it in a way that the formula for it looks very much like a formula that should look very familiar to all of you. It looks like the wave equation that you have in electromagnetism. And of course, the difference is that it's gravitational waves, not electromagnetic waves, but the form looks similar. And so this little h mu nu is what we measure. It's the amplitude of the gravitational waves, and it's very similar to the wave function in electromagnetism. And we know that in electromagnetism, when we have a form like this, that it creates a plane wave. So you have a plane wave that travels at the speed of light. That we have the speed of light in the formula above. And for gravitational waves and for electromagnetic waves, we expect it to travel at the speed of light. If you look at the picture here, then there's two components of the gravitational waves, just like there are in electromagnetic waves, only with one difference. You notice that the two components are at 45 degrees from each other instead of 90 degrees from each other. What that means, why that's true is because gravity is quantum mechanically spin 2, while electromagnetism is spin 1. So in electromagnetism, you have two components that are 90 degrees from each other, representing spin 1, and here you have two that are 45 degrees from each other. We haven't yet been able to just experimentally decompose these two components of gravitational waves in data yet. It's one of the goals we have, and I'm sure we'll accomplish it soon. In order to do it, we need three, not two detectors like I showed you, but three detectors that are pretty comparable. And there is 33 detectors in the world, but the third one that's operational and best is in Italy, and it is not nearly as sensitive as LIGO, so we're not quite able to do that yet. When it's more comparably exposed to the two. So that's basically a result of the fact that gravity is spin 2, and we have two components, as I've shown here. That's all I'm going to show kind of in terms of kind of theory or physics. Now let me talk about what kind of astrophysical phenomena will make gravitational waves. The one I showed you already, and the only one that so far has been definitively detected, is the merger of two compact objects. The two compact objects that we've detected are the merger of a pair of neutron stars, and we've also seen the merger of two black holes. In fact, the first event that we saw was the merger of two black holes, and most of the events that we see are merger of two black holes. We've also seen examples of a merger of a black hole and a neutron star that are coupled together, but I won't talk about any of those today. The search technique that we use is called match templates. I may just describe that for a second. So what we expect is to see a merger where the form of the wave is illustrated on the right. If the objects are fairly light, you get something like the very top one. In our frequency range of LIGO, which is the audio band, we would detect quite a few oscillations and be able to calculate those by Einstein's equation. If they're very heavy, like the bottom picture, then we will see fewer oscillations. And in fact, the very first one that we saw was very much like the bottom one in this picture. There's other sources of gravitational waves. I'm going to pick one to talk about today, but I'm just going to mention that there's bursts of gravitational waves. We've seen the merger of two neutron stars, which gives a gamma ray burst, which is a burst signal. And so that's a second one, or it could come from, for example, a supernova. Third one is pulsars, just a pulsar that spins in our own galaxy. Pulsars are generally measured by radio telescopes. They're very constant in time. I'll come back to that a little bit later. But we haven't seen directly yet a signal of gravitational waves coming from a single pulsar. It's one of the main things we're looking for. Is very difficult because the pulsars that are well known are already very, very spherically symmetric and won't give very large gravitational waves. And so the process of finding ones that haven't yet become very symmetrical is the challenge that we're doing. The fourth subject, which is probably in many ways the most interesting, is that looking with gravitational waves at the sky, we know that only 4% of what's out there is in the form of matter or energy, matter that we understand, and the rest of it is what we call dark matter or dark energy. We also know that by looking at what we see, we're only able to see something that emits electromagnetic radiation. And so you must expect that there's many phenomenon that will maybe give gravitational signals that don't necessarily give electromagnetic signals. And we look for those, and I'm not going to have time to talk about those today. We haven't discovered any yet. The last is signals from the early universe, and I am going to talk about that today, and what I'm going to kind of preview as what I think is, in the long run, the most interesting subject of all with gravitational waves. But you can see from the whole page that I have here that the potential in gravitational waves mirrors what we know in electromagnetic waves, and that it is a very rich science covering many, many different things. And we're just barely able to detect gravitational waves at the present time, so we're not able yet to look at many of these very interesting things. And that's left for people like you students as the field matures over the coming years. Okay, so let's talk about gravitational waves themselves, how we detect them, and then I'll talk about the early universe now. Gravitational waves themselves are ripples in space-time that stretch and compress space-time itself. So listen to that very carefully. It's a function of space and time itself. It's not like electromagnetic waves that are photons or waves that are traveling through space. These are actually ripples in space and time itself. So there's not, as far as we know, anything equivalent to the photon. We look for whether gravitational waves have a carrier, the equivalent of a photon, which would be called a graviton, but we don't see anything. We don't expect to, but we don't see anything down to very, very tiny masses. So the ripples in space and time itself, distortions of space and time. We're used to seeing distortions in space and time. We do it in astronomy, in looking at gravitational lensing, for example. So that's the first thing. The amplitude I mentioned earlier is tiny. So the amplitude of a typical phenomenon that gives gravitational waves is of the order of 10 to the minus 21, a very tiny number. And without talking about how you measure it, anything measuring something that's that small is difficult. The change of distance between masses that are free to move by gravity, free to move, is what we do. And space-time is so stiff that the changes in the distance are very, very small. So that's kind of what happens. And I illustrate this here by the size of the gravitational wave signal being 10 to the minus 21. So as I said, kind of in words, and I'll just repeat that again, an interferometer looks like this. Light coming in from a laser is split with half of it going in one direction, the other in the perpendicular direction. The total length that they travel is 4 kilometers. And if they come back at slightly different times, then we're able to see the gravitational wave signal. The gravitational wave signal itself will evolve in time, which is shown on the bottom, with first being elliptical vertically, say, in this picture, and then horizontally. The time between it is, of course, it depends on the frequency or the wavelength of the gravitational wave. And the installation to do this, which I won't talk about today, is 4 kilometers long. This is a picture of LIGO, so you at least see what it looks like. There's 2 of them, one in Hanford, Washington. That's in the Pacific Northwest of the U.S. It's in the topology is what we call high desert. So it's fairly high altitude, but it's a desert kind of environment, which you see here. and so it's flat and pretty stable. The second interferometer is in the state of Louisiana, a little village called Livingston, Louisiana, and it's sea level, and it's very moist and wet compared to desert. This channel right here is water, and it's next to the interferometer itself because the interferometer was built up onto a berm about 5 meters high by taking water next to it in a trench, and that trench fills up with water. So the water table is very near the surface, and all the outside area that you see here is a pine forest, where they cut down the pine trees periodically in order to make paper in the U.S. The buildings in the center are where the laser is, and the operating room, and where the staff has offices and labs and so forth. And it looks pretty much the same in both sides. So let's talk about just for a minute what limits an interferometer and why this is so hard. So this is a schematic of an interferometer itself. You can see the laser beam comes in from the left. It hits a mirror which is half silvered. By half silvered, it means half the light goes through it, half the light gets reflected. And so half the light goes one direction, half the light goes the other direction. As I said, if it comes back at exactly the same time, with no gravitational wave, there's no signal in the photodiode here. But if one arm gets slightly longer or shorter than the other, they come back out of phase, and this photodiode sees the signal, and that's the way we see the effect. I'm not going to talk about the interferometry today. It's very sophisticated, but it's a different talk. But I will say what limits this. So why we can't just make it more and more sensitive? What is it that limits it? First thing is residual gas scattering. So if you go down one of these arms, they're 4 kilometers long, there's atoms. There's even atoms if we have vacuum. So there's some scattering off the gas. If it scatters, then the path to go down and back isn't just a straight line, and so it can make signals that are out of time. So we have to make LIGO at what's called high vacuum. That's in the units that are used in vacuum technology. We're at 10 to the minus 9 torr. That's the highest vacuum that usually exists in laboratory experiments. What's difficult for us is done on a huge scale of 1 meter, 1.2 meter wide diameter tube that's 4 kilometers long, and it has to be at high vacuum. The second limitation comes from the laser itself. So even though we have very fancy lasers, and you all use lasers, laser pointers and so forth, and lasers are phenomenal in how accurate they are, they're not good enough for LIGO. So we actually introduce a lot of extra electronics in order to stabilize the laser well beyond the normal laser light would be in wavelength, in amplitude, in pointing, and so forth. So that's the second limitation. The third one is that the mirrors on the ends have to be held somehow, and so they're at least somehow attached to the earth, or they feel the movements of the earth, and that's called seismic noise. And it was the most difficult problem that we had to become sensitive enough to detect gravitational waves. The next one is what you might call thermal noise, which you learn in school, KT noise, and that's the fact that the mirrors themselves are made out of atoms, and the atoms move around at room temperature, and that causes not to be a totally stable mirror, and that's called Brownian noise or thermal noise. The last one that I'll talk about is the most interesting, because we all know that quantum mechanics is the most interesting, and this is the dilemma that in order to get a more and more sensitive signal, we put in a higher and higher power laser, and that makes more and more photons that are hitting the mirror. But the photons that hit the mirror actually push on the mirror or create a radiation pressure. And so in order, and that moves the mirror a little bit. So there's a trade-off between moving the mirror by having more photons or having less photons, and that's called quantum noise and or shot noise, and that is the last one. All of these we can't eliminate, we reduce as far as we can, and in order to get below where we can detect gravitational waves, and that's shown in this picture here. So in this picture here, you see the shaded region. First, it looks like what I've shown before, the sensitivity on the left. You can see 10 to the minus 21 here. And on the right is the frequency of the gravitational wave. All the lines are the different lines that come from what I showed you in the previous slide. And that is the lines of where we are in our design in getting rid of thermal noise or getting rid of gas, which is shown here, thermal noise. The intersection of all of those is the limitation, is the limit of how well we can do measurements. And so the measurements can be done in the region that's shaded up here. And you'll see that it's limited at the lowest, and what we're showing is frequency versus sensitivity. And what you see here is that the lowest frequencies were limited by the shaking of the earth, seismic noise. And the highest frequencies were limited by what's called shot noise, which is photostatistics, how bright the light is in the laser. And in the middle, we're limited by KT noise, or what I call thermal noise. So all of those play a role. And the sensitivity that we need is below this 10 to the minus 21 to make detections. And we continually try to make the detector more and more sensitive to get down into the regions here. And to do that, we have to fight all these technical features. This shows us being able to do that. So this is based quite a while ago, but it illustrates the fact that we see a signal that keeps getting better and better in the different colors, all space and time, where we measure how well we're doing, take some data, and then what limits us, fix that, and then it gets better and better. And eventually we get down to the very near this one, the design level, the design is the line here. And you can see that the scale here is this is an early one, the scale here is 10 to the minus 19. So that's the scheme. The sensitivity that we want to measure is 10 to the minus 21. That's equivalent to a movement in length over 4 kilometers of roughly 4 10 to the minus 18 meters. That's about 1/1000th the size of a proton. So we're trying to measure something that's really smaller than atomic scales or nuclear scales. And the two most sensitive problems that we have is we have to do the interferometry to 1 part in 10 to the 12th of the wavelength of the light. That's the challenge we have, and we have to make the interferometry well enough to do that. And the second biggest challenge we have is we have to float this relative to the Earth, even though we're working here on the Earth, such that we reduce any vibrations from the Earth by a factor of 10 to the 12. And basically, meeting these two goals is what took the very sophisticated equipment and the time it took us to go from beginning this project in 1994 to success in 2015. So 21 years was not just building an interferometer, but doing all the improvements that were needed to do that. This, for example, is the seismic isolation system that isolates this from the ground. And when you look at this, you can see that it's a combination of shock absorbers, which are these jagged lines, and a feedback system that measures how much it's moving and pushing back against it actively. And that takes the mirrors themselves and reduces the motion from the Earth by a factor of 10 to the 12th in actuality. So this took a long time to develop, even though it's basically not a fancy physics system. It's a mechanical system with some feedback, but it was the biggest challenge other than the interferometry itself. Okay, so let's look at the signal, and then we'll look at the first signal. So this is what we expect. During the in-spiral phase, this is time going to the right, the size of this little h, or the signal here. So if two objects are going around each other, they're publicly spinning, as shown here, and they're trapped around each other, like the Earth around the sun. And as they're going around, as they get closer and closer, the gravitational wave signal gets larger and larger, and the frequency gets higher, so they get narrower. So it goes like this, or it gets narrower. Then they merge together, and during the merger itself, that's in the region in general relativity, which describes Einstein's general relativity, which describes gravity and the strength of gravity very strongly when they're merging together. And that's very difficult to calculate, and maybe is the most interesting in terms of us understanding general relativity itself, testing Einstein's equations against other alternate formulations of general relativity. Once it's merged together, then it rings down, and that's, again, characteristic. Over here on the right, it shows the difference between if we have two light objects or heavier objects. Light objects will go to high frequency, and we'll see many oscillations in our interferometer, and the heavier ones will only show a few, like the very first event that we saw. So we then look at the space of masses that the objects could be that are merging together, a binary set of objects, one solar mass, five solar masses, and so forth. And we calculate using Einstein's equations what the signal would look like everywhere in this space, and then we compare that with the data. And that's the way we basically pick out the signal. When we've done that, this is the data from the very first event. So the very first event, the data is shown in Hanford, Washington, in the upper left, in Livingston, Louisiana, the upper right. These are within milliseconds of each other in time. This is the calculations of Einstein for a merger, and you can see by eye that it looks very much like this. And the most important part of this is to subtract one from the other, and you see what I show in the very middle, which is just jagged noise. That indicates that this theoretical description by Einstein is a wonderful, captures the physics that's in here and here, because all that's left is just the limitations of the instrument or the noise. The bottom is just the time versus frequency distribution for each of them. And we can describe from Einstein's equation the what this shape will look like. And I've written the first term here. There's more than one term. And with that, we can calculate most of the features of the gravitational wave, from the orbital precession to whether it's spinning, to the masses, and we can tell how far away it is by the size of the signal, and so forth and so on. When that's all done for the first event, we got the signal, which is 36 solar masses for one of the objects, 29 for the other. That adds up to 65. But the very final object that we see oscillating is 62. And so the difference between 65 and 62, which is 3 solar masses, is the energy that was radiated away in the form of gravitational radiation. And this is how far away it is. It's about 1,000 million light years. So it's about 400 kiloparsecs. Okay, now that is we've done much more with chirps. We now have maybe 300 illustrations of some sort of a merger, like the one that I showed you. I'm not going to talk about those anymore today. Instead, let's talk about the other sources, and then I want to pick one to just end this talk. A second set of sources would come from the collapse of a star, like a supernova. We haven't seen that yet, at least not. There hasn't been a supernova in our own galaxy during the time we've been observing, but that's the second kind of signal. Third one is the periodic signal. I mentioned this before. That's just pulsars in our own galaxy spinning. This is challenging to measure because the ones that are going to give a big gravitational signal haven't yet settled down to a fixed frequency. So those sources haven't been seen by radio telescopes, and we have to find them with our own searches. And so far, we haven't seen one. The most interesting, probably of all, that I have here is the fact that we're looking at the sky in a completely new way with gravitational radiation instead of electromagnetic radiation. And so it seems very likely that there's objects or phenomenon that happen that give gravitational radiation, which we haven't ever seen with electromagnetic radiation. So we don't know how to model their physics like we did in the ones, the three that are shown above. And so instead, we have to look in some non-prejudiced way for new sources in the sky. So far, we haven't seen them. It's very difficult to look for what you don't know what you're looking for. But I'm not going to talk about that either today. I want to pick on this as my last topic to end the talk. And it's maybe in the time period of this audience and maybe physics and astronomy and astrophysics and cosmology, the most interesting subject for the coming tens of years, I think. And that is to look and study what, with data, what happened in the very early universe. So this is a very popular subject, long-running comedy that's been on television for 12 years. And it's very popular, called The Big Bang Theory, just about, it's a comedy about a set of young people who are looking for understanding the mysteries of the early universe, the Big Bang. This is what we know, or what we think we know. And so this is a picture of the evolution of the universe from, on the left, the hot Big Bang, to where we are today, 13.77 years later, at the very, very right. So starting from the left, we know from indirectly, we know that the Big Bang itself was what we call a hot Big Bang. In other words, it started with a lot of energy. It didn't build up after it started. So it had a lot of energy from the very beginning. And then there was a period of very rapid inflation. This is an expansion of space and time itself very rapidly. So it doesn't exceed the speed of light or anything. It just expanded very rapidly. We call it inflation. We don't really have a good understanding of it because it goes back, it's happened, except that it was there because it happened so early in time. I'm going to come back to how we might get at that in the future. And then eventually we start making particles and they interact and so forth. And the universe was basically opaque to light until 375,000 years after the Big Bang, at which point you start to be able to see the signal. Superposed on this, you can see something in different colors. I'm going to come back to that. That's our best picture of what the early universe looked like. It's called the cosmic microwave background signal. And it's at 375,000 years after the Big Bang. And it's basically a snapshot of what things look like at that time. And I'll come back to it. After that, we just have some particles. So they haven't combined to do much yet. And eventually they form stars. And that starts at about 400 million years. And then eventually they form not just stars, but galaxies and come to the universe we have today. You'll notice that this is expanding. It's getting bigger across as we go out. But at the very end, it curves out again, meaning it's expanding more and more rapidly. That's what we call the accelerating expansion of the universe, or what's called dark energy now. And so that's a picture. It's all 13.77 billion years old. And the question I want to address is, how do we get more information on what happened at the very earliest times, how our universe formed, and what happened then. And so the big questions are, what was the hot Big Bang? Because I'm using the word hot there. What really was it? What happened at that point? Because that's a fundamental question. What was this inflation that I talked about where it inflated very, very rapidly? A third question, which I kind of rhetorically have here, is why are we here? That's the question which we can't answer today of the energy in the very beginning by Einstein's equation E equals mc squared turns into masses. But from everything we know about the theory of particle physics or the collisions that we look at CERN or studies of exotic particles like neutrinos, that there's as many particles as antiparticles made at any given time. If that were true in the early universe, we would have made as many particles as antiparticles. They would have annihilated each other and we wouldn't be here. So somehow there was a small asymmetry in the early universe where there was more matter made than antimatter. When everything annihilated, we're left with matter. And we now have a universe that's dominated by matter. And we don't understand that. We have some ideas, and we're looking at various experiments that can give us some more information. To find the answers, we have theory, of course, theoretical ideas and different theories of what it can be. What we need, and what I'll address just briefly to tell you how we're trying to do it, is probes of very early times. That's experiments that can give us information on what happened, is to recreate the universe and understand that physics. And finally, independent of everything I've said, we have to keep in mind that when we go into physics, somewhere completely different, in this case, the early universe, we have to keep in mind that maybe the laws of physics that we've learned here in our local universe may be different. So there may be violations of the laws of nature that we know, and we have to keep our eyes open to make sure that that's not true. So first piece of the puzzle has been answered, and that is the famous experiment done at CERN in 2011 that saw the Higgs particle proved theory that we had on how Einstein's equation E equals mc squared works. How do you make mass from energy or energy from mass? And we know that Einstein told us that in the early 1900s. We know that it's true, and people even made fission and bombs and things by doing this, which it's done, was proposed in the 1960s by Mr. Higgs and several other people. And it was proven by seeing the particle that's responsible for it. This is the data from CERN that showed that it's a particle called the Higgs particle now, which is at 120 some GeV. That's 120 times the mass of a proton. And it gives us information on the origin of mass. And it's in the spirit of what I'm talking about now. And that is to try to find the different pieces. Now we know how you make mass from energy, how you make those particles, the quarks, and so forth in the early universe, at least in terms of how the energy changes into mass. Second question about the early universe is interesting, and that is at the very early times, 100 years ago, a little more than 100 years ago, Einstein proposed that the universe was what he called a static universe. And that is that it was always the same. That has a problem in terms of stability, because if you move a little bit off of it, if it expands just a little bit, or there's some asymmetry somewhere, it's not stable. But that was his proposition. Hubble, 100 years ago now, found evidence that the universe expands. He just looked at how fast objects were moving away from us as a function of how far away they are, and saw the graph that is shown here. And that gave us Hubble's law, which is shown down here. the original measurements of the number weren't right, but it's about 70 kilometers per second per megaparsec. So that's the expansion of the universe. We know that it's doing that, expanding at that velocity. And that was seen about 100 years ago. Second piece of the puzzle that was seen in just almost 100 years ago in 1933 was found by this gentleman here who was at my institution, Caltech. And he studied the redshifts, that's how fast things are moving away, of various galaxy clusters. And he noticed there was a large discrepancy or scattering of the apparent velocities of 8 different galaxies in the Coma cluster. And he estimated the cluster masses using the virial theorem, which we all know from physics, that connects potential and kinetic energy of a system. And he expected to see a dispersion of these velocities of about 80 kilometers a second, but he found something that was 10 times that along the line of sight. He said in his article, if this would be confirmed, we would get the surprising result that dark matter is present in much greater amounts than luminous matter. That he published in 1933, and nobody paid it any attention. It was almost 30 years later, about 30 years later, that Vera Rubin, Kent Ford, and Ken Freeman came back to that problem and looked at it much more scientifically. And they looked at the the velocity of objects in the rotation curves of, for example, the spiral galaxy. They worked with a spectrograph to measure the velocity curves of edge-on spiral galaxies. And what they found was that as you move further out in the spiral, you expect there to be less mass and things are going to slow down. But instead, they move as if there's much more mass there. And that paper they published in 1978, 1980, and they showed that most galaxies, they concluded, contain at least 6 times as much dark matter as what you could see in, for example, a spiral galaxy. So by about 1980, we knew the apparent need for dark matter, and it was widely recognized as a major unsolved problem in astronomy. I don't have time to show you other pieces of evidence along the same way that show that what the dark matter can't be, and that it has to be some form of matter that's different than normal protons and baryons and so forth. But this is the curve. So in a spiral galaxy, you expect the rotation velocity to speed up to a certain velocity. But as you go out further from the center, it should fall off as there's less mass around, and instead it's observed to hang up. And that was the illustration that there was dark matter. The next piece of information that we've had recently, actually 2011, was what we call the discovery of dark energy. That was done by these 3 gentlemen, Brian Schmidt and Adam Rees, working together in one collaboration, Saul Perlmutter in the other, but both trying to do the same thing, which is to measure today what the expansion velocity is of the universe, and whether it's contracting was what they were trying to see, or just constant. What they found instead is that it's expanding. And so basically you can see that this here, where I show the redshift, that's how fast things are moving away, how far away they are in time versus the distance. And you see as we go up the curve, it follows a straight line, but then falls off to the right. Falling off to the right means that if you go back in time, these are the parts of the universe that are further away from us in distance, 3,000 megaparsecs, they weren't going as fast. The redshift is less than the continuation, which means if we go back in time, the universe wasn't expanding as fast as it is today. And that's the evidence that the universe, the speed of the universe, the rate of the universe's expansion is accelerating as we go through time. So we now have this picture that people have seen, which is the dark energy. What they just saw is most of what's in the universe. We don't know what it is. Dark matter is second, 23%. And then we only have 4% that's made of matter, normal matter that we know. So how do we now pursue this subject? And I want to end on that and then I'll be done. So we pursue this subject by first looking now, and I see in the bottom right the picture of what the universe looks now. So astronomers look and they look at galaxies, they look at early stars now and try to understand how it all evolved to get us a picture of what the structures are in the universe and a fixed point that whatever we pick and how it's evolved, it has to match what we see now. If we go back a little further in time, then we discovered in the past that the cosmic microwave background, which was accidentally discovered, can give us basically a picture of what the universe looked like as far back as we can go with electromagnetic radiation. That is 380,000 years after the Big Bang. Before that, the universe was opaque. So that's the point at which we have a picture. It's not uniform when you look in detail. That's what the different colors mean. And it's those differences that basically, in the end, enable us to develop into different galaxies and things because we don't have a completely normal universe now. And the theory that we have about the expansion of the universe and cosmology comes from much of it from this and what we can observe later. We know, as I mentioned earlier, that there was inflation at an earlier time. So, and then at the very beginning, the hot Big Bang, where we made cosmic gravitational waves and cosmic neutrinos. So let's look further. How are we going to probe better? What we want to do is go back earlier than 380,000 years. First, the 380,000 years, I'm running out of time, so I will just say it quickly in words. Were discovered accidentally, this picture, by these two gentlemen, Wilson and Penzias. In 1965, they accidentally discovered this microwave background. And then there's been beautiful satellite experiments that have seen the shape of it. And now we look at the little asymmetries that exist. And for example, this is from the Planck satellite. So that's our picture at 380,000 years. And one of the things that we're trying to do is look in the next generation of these cosmic microwave background experiments of whether there's any indications of particular features in this distribution that indicate a possible effect that would come from the interference of gravitational waves and electromagnetic waves, what we call a polarization. And that hasn't been seen yet, but it's the big goal of these cosmic microwave background experiments in the next generation. Better yet, so setting that in detail is a big goal. Better yet would be to probe to earlier times. So I'm talking now about we were doing photons and we have the cosmic microwave background, the signal shown in these pictures here. We could go to earlier times using neutrinos. With neutrinos, we could go to 1 second after the Big Bang when you were starting to form particles, quarks, leptons, neutrinos. And so that is what we would hope to do. It's a very, very difficult problem because the neutrinos that came from that time are very, very low energy. And so they're hard to detect. This shows that there's lots of them, but they're very low energy. This is the energy of the neutrino versus the frequency or how many there are. The cosmic neutrino background is the one on the very left. You can see it's the most prolific. There's more cosmic neutrino background neutrinos going through your hand right now or yourself than any other form by orders of magnitude. But they're so low in energy, you can see it's below 10 to the minus 3 eV, that it's very difficult to, but not necessarily impossible to detect them. So people are working to build possible ways that you can detect them. And but we don't have that yet. And that's the challenge for you and for the future. The second possible way to get it even earlier in time is to look for gravitational waves that came from the very first instance of the Big Bang. And that'll go back to the dawn of time itself and go back to the very beginning. So it's not seconds after like neutrinos, but actually during the hot Big Bang itself. We can't do that yet either, but we're starting to do better. So LIGO is shown here. This is a plot of frequency per hertz. And so LIGO is way out on the right. It's high frequency. That's the audio band where we measure the frequencies of gravitational waves that are frequencies like radio waves, our voices. We're going into space soon, and that'll go to lower frequencies by several orders of magnitude. And that's called LISA, and it's approved to be flown about 10 years from now. And a third way to go even lower is to use nature itself to do our detections for us. And that is to use the fact that pulsars are very good clocks. If we have a lot of pulsars that we monitor at the same time, and they're such good clocks, and a gravitational wave comes through, it'll distort the relative magnitude or time on those clocks. And the people are trying hard to do that. And this is a picture of the data recently released, which shows an indication that they may be seeing signals from gravitational waves. These signals maybe didn't come from the very earliest times yet. They likely came from big black holes, but nevertheless, no signal would be just a straight line. The expected shape of a signal is the dashed line, and you can see the data looks like that. It's not yet 5 sigma. The source is probably not cosmological, not the earliest times, but it comes from early black holes. But it's again the way we're probing to go to early times and the challenges of the future. And so overall, with gravitational waves, we're presently on the very right-hand side of this diagram. But like electromagnetic waves, where we've kind of covered from radio waves up to high energy photons, with time, we'll do the same with gravitational waves. And as we move more toward the left, as I just illustrated, we move to where we can start and hope to do measurements directly with gravitational waves of the early universe. And lastly, I want to say one other thing, and that is there's one other way to probe the very early universe, and that is to recreate today the conditions that existed at that time. And we do that by a combination of the most modern devices that we have. And I show them together kind of symbolically, at least on this graph. This graph has temperature versus density. And you can see on the left, at very low density, but very high temperature, meaning high energy, the hadron collisions that are done at CERN, very high energy colliders. So we get information on this part of this plot from CERN. If we go to Brookhaven, where they have heavy ion, then they make the quark gluon plasma. That's this region out here. And so we get information that goes there. We can study nuclear matter, like the collision of neutron stars. That gives information here. And all the work we do on gravitational waves, the merger of objects is in this region here. So in some sense, we're starting to be able to cover the space that would cover the physics of temperature versus density that covers the same kind of space that would exist in the early universe. So this is the last way we have of probing the early universe, is to recreate the conditions of the early universe itself. And with that, I thank you.
Thank you so much, Professor. That was a wonderful, very informative talk. Do you have a few minutes for some questions?
Sure. Can you get me back? Let me stop sharing, maybe. See. Okay.
So I'll just allow people to unmute so that they can ask their question according to the order in which they're come.
Okay.
Yeah, Adam, you can go ahead with the question.
Okay. Somebody talking?
Okay, he says he doesn't have the mic at the moment. I'll just read out his question for you.
Okay.
Several recent proposals suggest that teleportation-style protocols or measurement-based schemes to realize effective frequency-dependent squeezing without long filter cavities. Do you see this as a future for LIGO rather than the present filter cavity approach?
Yeah, we're already incorporating. The answer is yes, and in fact, it's maybe an illustration of the general problem. We've made a classical interferometer. We try to deal with the limitations of a classical interferometer in the best ways we can. But then we hit limits, and we already hit a limit that I mentioned, which is it doesn't quite get to what his question asked, but it's the right direction, which is that we can't do any better with just putting more light in because we basically put more pressure on the mirrors, and so we can't get a better measurement unless we do something about the conditions of that light. So we do what we call squeeze light, which is basically the first step in what he's talking about. And that changes the pressure, reduces the pressure while we can increase the number of photons on the signal. And we've done that, and it gives us, at high frequencies, about a factor of 2 or 3 gain in sensitivity already in what we've done. And by a lot of special R&D, we've taken the natural effect that this works at high frequencies and been able to extend it to the lower frequencies that we measure in LIGO. So the recent improvements in the sensitivity of LIGO are due to these quantum effects or squeeze light effects, which is a first step along the way of making something more like he's talking about.
Thank you so much for the answer, Professor. Anybody else, any questions? So we have another question. How are we able to receive gravitational waves from very early universe which have occurred a very long time ago? Shouldn't the wave have already passed us in the universe?
No, because the universe keeps expanding. We're not at the center of the universe where it's gone away. We're part of the expanding universe. So just like we look back to what happened it's no different than what we're doing with cosmic microwave background, which is basically giving us a picture 370,000 years after the Big Bang. You're going to ask why those photons haven't passed us. The fact is that we're part of an expanding universe, and we're not at the center. And so we basically can view back in time by just how far things are away from us and what their features are.
Thank you so much. I have a question myself.
Sure.
So, do you think the directional dependence of gravitational waves can be found out better than what we're doing with neutrinos or with SNUs to triangulate supernovae?
I don't know. I mean, right now the direction. I don't know why you'd want to know much better. I mean, but obviously telescopes do much better in astronomy. But basically, what we're able to do is tell direction by having multiple interferometers. So what I've shown is 3 interferometers. With 3 interferometers, we're able to do well enough to be able to correlate with electromagnetic radiation. That is, that we can do well enough that it enables us to use devices that point much better in electromagnetic radiation in a particular part of the sky without it being so broad that they can't do it. The modern instruments are more survey instruments. So the newest instrument, the Rubin telescope, for example, is a survey instrument. So it's not just looking at one place in the sky and you rotate it, but instead it covers accurately, but covers the sky. In terms of measuring accurately itself with gravitational waves, I don't know how to do it. We basically except for having multiple instruments and doing the relative timing, we can't do much better than that unless somebody comes up with some other idea.
Thank you so much.
Hi, so I had a question regarding, so I had a question and a follow-up question on the basis of that. So my question is that what is the frequency scale for the early universe gravitational waves?
What is the frequency?
Frequency scale as in that the LIGO works with a higher frequency level. So the detection on the basis of, like, if we are saying for early universe scale, what would be the frequency scale of those gravitational waves?
Yeah. I could, if we went back to my plot, I could show you, but I don't have the number, but it's very, 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 very low frequency. So that's
Yes.
why it's
Okay. Okay. So the follow-up question is that since LIGO only works with a higher frequency and higher energy gravitational waves, so won't using the PTA signals be more beneficial in detecting the gravitational waves for early universe?
Well, which signals?
The pulsar timing array signals, like the pulsars sending radio waves.
Pulsar.
Yeah.
Yeah. So the problem is, it's an interesting question because I don't have my slides in front of me, but it's sensitivity versus being in the right place. So we know how to make things very sensitive at the very highest frequencies, but the signal is going to be smaller at those highest frequencies. But if we go to lower frequencies, the signal's bigger, but our ability to measure is not as good. So if you go to pulsars, they're not, or even in space, their ability is not as good as we're able to do here. So it's a trade-off between being able to measure very well and being lower frequency where the signal's larger.
Okay, got it.
Okay.
Thanks so much.
I think I'll just read out one last question from the comments and we can close after this. So the question is, what results do you expect from third generation gravitational wave detectors like Einstein telescope, and will it have better sensitivity than the current advanced LIGO and Virgo?
Yeah. So I didn't talk about it directly here. We're on a, let me just say, we're on a program for the next 10 years, 5 to 10 years of stepwise improving LIGO's sensitivity. The next step is to build a new detector with 10 times the sensitivity, more or less, of LIGO. What that'll enable is to basically begin to do, at our frequencies, cosmology. That is, everything we do right now is at a redshift of 1 or less. And so we're not in a region of where we're looking back in time or where the redshift is high, which is when you can do cosmology. But with the next generation gravitational wave detectors, for example, we'll be able to detect black holes back to the beginning of time. Neutron stars, maybe not quite that far, but further. So for me personally, the biggest, and you can tell from what I talked about today, I think the biggest gain in going to the next generation gravitational wave detectors on Earth, the ones we're talking about like that, it is not going to be the fact that we can detect so many good statistics, gravitational waves, but rather that we can actually start to do directly cosmology, high redshift studies with gravitational waves, even at our own frequencies.
Thank you so much, Professor. So, if I think those are the questions, I think we can close the meeting now. We thank you again for the wonderful and very informative talk. It was a great experience being able to listen to a person of your experience and valor. So, thank you once again, and thank you.
Good luck to all of you, and have a great.
Sorry to interrupt, sir. Can I ask a question?
Yeah, who's talking?
Shivansh.
Somebody wanted to ask? Yeah. Did you want to ask something?
Yes, sir. How neutrinos are affecting the real world and can they alter the reality?
Say that again slowly?
How neutrinos are
How neutrinos are doing what? You broke up a little bit. How
I
neutrinos
think this is not working properly from the chat.
I can't quite if somebody else can hear it, you're breaking up. I can't quite hear what she said. The question was about neutrinos, but I didn't hear what it was. How neutrinos can.
I think it was something about how neutrinos can alter reality, if I heard it correctly.
Oh, can alter reality. That's beyond my expertise. I don't know. Okay. Anyway, let me thank you all and have a good day and a good life.
Thank you so much, Professor.
Thank you, Professor.
Bye bye.
Bye.